Problem B9 is about the same problem as B8, but here at B9 it is asking what is the mass moment of inertia about y-axis or z-axis. Because of symmetry, mass moment of inertia about z-axis and y-axis, they're going to be the same. So we need to just find one of them. Now, how can I find the mass moment of inertia about y-axis? What element should I use? Of course, you have different options, but probably the simplest one is using parallel axis theorem. What's the meaning of that? If you choose the same integral element, a disk, with the distance of x from the origin, and so we are choosing the same disk as previous problem, and I need to find the mass moment of inertia of this element about y-axis, then integrate that to find the mass moment of inertia of the whole object about the y-axis, right? But we know the mass moment of inertia of a disk about this axis is going to be 1/4 times mass of the disk times the radius squared, right? We showed that in previous videos. So I about this axis is going to be 1/4 times the mass of the element, which is dm, times the radius of it squared, which is y. Using parallel axis theorem, I can find the mass moment of inertia of the same disk about the y-axis. Because this axis is passing through the centroid of the disk, I'm allowed to use the parallel axis theorem. So I about this axis of this tiny disk is going to be this I plus the mass times distance squared, which is x. So I about this axis is going to be 1/4 times dm times y squared plus mass, which is dm, times the distance squared between the axes, which is x. This is diy, the mass moment of inertia of my elements about y-axis. Now, if I integrate these two sides of this equation, I'm going to be able to find I, y. So let's write that again. diy is equal to 1/4 dm y squared plus dm times x squared. And we know what is dm. We have the equation here. We can replace dm with rho pi y squared times dx. Then because we have dx, we need to write everything in terms of x to be able to do this integral. So here I'm going to have 1/4 times dm, which is rho pi y squared times dx times y squared. So I'm going to have y to the power of 4 here. Plus dm, which is again rho pi y squared times dx times x squared. And we know based on that equation, y is equal to k times x squared. X to the power of 1.5. We know this equation, so I can replace all the y's with k times x to the power of 1.5. If I do that, then diy is going to be equal to 1/4 rho pi y to the 4, which is going to be k to the 4, and x to the 1.5 times 4 is going to be 6 dx plus rho pi y squared again is going to be k squared times x to the 3 times x to the 2 is going to be x to the 5. So k squared times x to the 5 dx. Now we can integrate two sides of this equation, right? Which is going to be quite simple. This part of it, we did it before, and the only thing you need to do this part. Then use the mass equation, which we found it here, to replace mass in terms of rho, pi, k, etc. And use k is equal to r divided by h to the power of 1.5. if you do all of that, just simple math, and I'm gonna leave it for you, then at the end I y is gonna be equal to mass times r squared divided by 7 plus 2h squared divided by 3. And also we know this is equal to izz because of symmetry. The mass moment of inertia, but y-axis is equal to the mass moment of inertia, but the z-axis.